Segment 15, Telescopes. Telescopes are the most important tool that astronomers use to find out about the rest of the universe. We're going to talk today about many different kinds of telescopes and some of the critical concepts that go together with our understanding of how telescopes work. Let's start by a little discussion of the night sky. This is a nighttime image of the United States taken on a clear night some years ago, and you can very clearly see the cities here. You can see in the middle of the country the whole Chicago area. As you move down to Texas, you can see the Dallas-Fort Worth area, and then Austin, and then San Antonio, and then in the lower right, Houston. And you'll notice as you look along this picture the highways that go across the country by the strings of little dots for the different towns along the way. Also notice in the western part of Texas, one of the darkest parts of the United States. This is the area where the McDonald Observatory is located. This picture shows you something of the problem of astronomy, which is 60-some years ago in 1950, the whole western United States was essentially dark. By 1997, the eastern United States is totally light at night as parking lots and Walmarts and everything open all across the country and spread outdoor lighting for all kinds of reasons over huge areas as safety concerns and other reasons of convenience became important, and the night sky essentially disappeared. This is important not just for astronomers but for the rest of us. On a given night, when you go out and look at the sky now, it's bright and you can't see the stars or the Milky Way or anything like that like you used to over most parts of the United States. Note, however, that the region in western Texas is still one of the darkest places available, and the prediction that you see at the lower right indicates that it will continue to be so. When we talked about forming images with telescopes, we had an illustration of a reflecting telescope, a reflecting mirror, that formed an image in front of the mirror. This is very inconvenient because, of course, it means that you can't really get at the image. So what astronomers do is put a second mirror before the focus of the telescope that spreads the light out a little bit and pushes it to a focus that's behind the mirror. This is called a Cassegrain Telescope. And in this kind of telescope, a small hole is cut in the center of the mirror to allow that light to penetrate through. The secondary mirror blocks a bit of the light coming in, but the fraction of the area is fairly small, and this is not a major effect in exchange for a significant convenience in terms of where you can now put the instrument or your eye when you want to look through this telescope. So with experiments where we put a CCD at the telescope focus, we put it right at the place where the light rays come together. But your eye doesn't want to be at such a place because you need to form an image of what you're seeing. As a result, what most telescopes that are going to be used by a person have is an eyepiece, and this eyepiece takes the focused light and makes it back into collimated light, into parallel light. The reason for that is that that makes what you're looking at look like a distant object that your eye can then focus on. The net result is that the telescope is concentrating the light, so making the objects brighter, and in the case of extended objects, making them look bigger. Here we see on the left a refracting telescope, a telescope with a lens doing the light gathering, and on the right a reflecting telescope where a mirror is serving that purpose. But effectively they amount to the same thing. They concentrate the light, and in the case of using an eyepiece, they also make the angular size of objects look larger to your eye, so that you can see more in the way of detail. Why are bigger telescopes better? The simple reason is that they gather more light together. Light gathering power depends on the area of a telescope. If you have a rain gauge, you know that the newspaper will sometimes say we had 3/100ths of an inch of rain. Well, if you have a 10 centimeter diameter rain gauge at the top, rain gauge is basically a funnel with a 1 centimeter wide test tube at the bottom, then if you got 1 centimeter of rain falling on your rain gauge, it would fill up that test tube to a depth of 100 centimeters. So even if you have 3/100ths of a centimeter of rain, that will fill up the test tube to a depth of 3 centimeters. And that's what gives you this sensitivity, this ability to measure very, very small amounts of rain. Same thing is true with a telescope. A telescope gathers together photons, and the larger the area of the telescope, the more photons from a distant object it can gather together. And this light gathering power is proportional to the square of the diameter of the telescope. Your eye, the opening in your eye, is at best a few millimeters across. If you have a telescope that's a few meters across, it can gather 1,000,000 times as much light as your eye, so you can see objects that are 1,000,000 times fainter. This is an impressive difference. The other advantage of telescopes is that they can improve your ability to see fine details in an object. The ultimate limit of this ability is diffraction. We spoke about this when we were talking about the properties of light. But if you have a finite size aperture, interference at the edges of this aperture limits your ability to see fine detail. The equation that we're showing at the bottom tells you what the limiting separation in angle in units of arc seconds can be for at a given wavelength given the diameter of a telescope. So what this says is that if the wavelength is in the visible range, for example, that's about half a micron, so about 5 × 10⁻⁷ meters, and the diameter of a telescope of a meter, say, then you have 2 × 10⁵ times 5 × 10⁻⁷, and that gives you about 10⁻⁻⁴, or about 1/10 of an arc second in the size. That's about 1/4000th of the size of the full moon would be your resolution. For telescopes on the Earth, however, turbulence in the Earth's atmosphere is what actually limits your ability to separate objects. This is an illustration of the effects of diffraction at the edge of a telescope. If you have a point source at infinity and you look at the image with a very deep exposure, you'll see a bright blob surrounded by a series of ever fainter rings, and this is caused by diffraction in the telescope. And this is now that the finite size of that center blob is what's now limiting your ability to distinguish objects. So for example, if you had two blobs next to each other, they would start to blur together, and it would make it very hard for you to notice that you had two rather than one once they got close enough together. Because of the problems with light pollution and the need for clear weather, we put our telescopes on high mountains, and we try to put them in very dark places. This is a picture of the Gemini telescope on Mauna Kea in Hawaii. Don't let the snow fool you. This telescope is at about 14,000 feet altitude, and there can be snow around it at any time of the year. This illustration of a 4-meter telescope at Kitt Peak National Observatory shows you the critical parts of the telescope. The primary mirror is buried inside that big white metal space you see there. The huge yellow yoke is part of the steering mechanism for the telescope. Going up the telescope, you have the option of either putting an instrument right where the primary mirror focuses it, or putting a convex mirror in and bringing the light down to the bottom of the telescope to the Cassegrain focus, where you can put larger instruments the way we illustrated at the beginning of this discussion. Telescope mirrors have to be extremely precise in order to form good images. They have to be curved exactly in the shape that you want them to be curved. But because they're heavy and you're tipping them around, they tend to bend. And there are two solutions to this problem. One is to make very thick, very stiff mirrors, but then they're extremely heavy and cumbersome. Or to make thinner mirrors with actuators that you actively steer to help the mirror maintain its form. And all modern telescopes are built this way. Telescopes in the old days were built by simply making them thick enough. So here you see an illustration of a monolithic surface that's too thin to support itself against its own weight effectively, and it's got a series of thrusters that are used to bring it back into its ideal shape. Another solution is to make this surface out of a series of small pieces, mirror segments, that can then be individually activated to keep them in line along a common surface that will form an image where you want the image to form. This is a picture of an actual telescope with somebody looking at it. You're seeing them in reflection. It's the Keck telescope in Hawaii, which has got a 10-meter diameter, and it's made up of about 70 segments. Here's an example of an 8-meter diameter large monolithic telescope. This is the Gemini telescope in Hawaii. And you see here this telescope with the primary mirror exposed, the secondary mirror up at the top, and then that hole I told you about that lets the light through to the instruments at the Cassegrain focus. I don't know if you can see it, but just to the right of the slit, which is behind the telescope, there's a thin little ladder. If you climb up this ladder, you can get out onto the roof of this telescope, and then you're 14,000 feet and some above the ocean in Hawaii. You'll notice ice on the ground, and there was about a 30-mile-an-hour wind, which is why what's left of my hair is blowing backwards. I've taken off my hat in this picture rather immodestly, but you get the idea. And it's quite spectacular to go out and observe with telescopes like this when it's not foggy and cloudy as it was when this picture was taken. This goes back to our discussion before. One of the main things we want to do with the telescope is not take pictures, but in fact break the light up into its constituent wavelengths. Here, ultraviolet on the left, infrared on the right. Splitting the visible spectrum up allows us to understand the physical nature of objects in ways that's not possible from pictures. And a lot of what we'll talk about over the next few weeks will revolve around this. In addition to visible telescopes, we have radio telescopes, and individual radio telescopes work somewhat differently. They can only look at a single point at a time. They gather the light together, and that signal is amplified and then recorded by a computer, and then by moving the telescope around on the sky, you can map out areas where it's brighter or fainter to produce a picture of the object, essentially 1 pixel at a time. So this is an actual photograph of a radio telescope in Australia. And it produces maps like this map of a supernova remnant showing you the emission of radio waves from the supernova remnant left over after the explosion of the supernova. There's another technique you can use in the radio, which is to combine the signal from different telescopes, many telescopes at once, and using sophisticated algorithms you can then produce an image of the object you're looking at that effectively is the image you would get from a telescope that's the size of the whole array of telescopes, not the size of an individual telescope. And if you remember back to that equation for the resolution, it was the wavelength divided by the diameter. So when you go to long wavelengths, having a very large diameter, as you get by adding together these different telescopes, helps you keep the resolution of the telescope very, very fine, which is what you want. Here's a picture of one of the largest of these kind of telescopes, the NRAO Very Large Array in New Mexico. This is on a plain in south of Albuquerque, and these telescopes can be stretched out so that at the farthest there's 27 kilometers between them, and they behave as if they were a single telescope that was 27 kilometers across. These individual dishes, which are 75 feet across, can be moved around on railroad tracks to put them at different distances from each other. We put telescopes in space. Here's the Hubble Space Telescope for 2 reasons. One is to be able to look at wavelengths that are absorbed by the Earth's atmosphere. With Hubble, that meant mostly ultraviolet light, but also some bands in the infrared. And also to get above the turbulence in the Earth's atmosphere that can disturb your observations. Getting above the Earth's atmosphere in the infrared means getting above the water vapor in the Earth's atmosphere, and since the water hugs the ground, it's much more concentrated than air in general. You can do a lot of the work in the infrared with a telescope that's only at airplane altitudes. And so a 2.5 meter telescope, about the size of the Hubble telescopes, have been built into a 747 airplane in an observatory called Sophia, and here you see a cutaway diagram of this telescope. This is an illustration of the aircraft, a 747 SP, a shortened 747. The telescope was actually built into that black space in the back, and a hole was cut with a door that can be closed for takeoff and landing, but is actually open in flight. The passengers, the scientists, are behind a bulkhead that protects them from the low oxygen content of the air at that altitude. In the original 747, the bathrooms were in the back, and you can't get there from here on this kind of plane, so they had to put in a new one up in the front, or let the scientists use the first class bathroom. Here's a picture of the 747 SP after it was modified. You can see the doors closed in this picture, and the chase plane is following along behind it. This telescope regularly observes from a base in California now.